In section 5.4, we're going to be looking at properties of logarithmic functions. So we are going to convert logarithms of products, powers, quotients to expressions in terms of individual logarithms and vice versa. We're also going to simplify expressions of the type log base a of a to the x and a to the log base a of x, and these last two are going to involve inverses. Okay, topic 1, logarithmic properties and rules. Our first property is the product property of logarithms. It says that log base a of the product m times n is equal to log base a of m plus log base a of n. It's a product property. This is similar to the exponential rule that says if you have a to the m times a to the n, you would simplify that to a to the m plus n. In the exponential rule, we know that when we multiply bases, we're going to add the exponents. In logarithms, since the answer to a logarithm is an exponent, we say that in a logarithm, if you've got a product, you need to separately add the exponents, the answer to the logarithm being the exponent. So that's just the corollary here, the relationship between our logarithm and our exponent rules. So in both of these cases, a multiplication is going to turn into an addition. Okay. Now, in the power property, we say that the log base a of m to the pth power is going to be equal to p times the log base a of m. This is similar to the exponential property, a to the m to the n is equal to a to the m times n. So if you have a power raised to a power, you're going to multiply the two powers. See how that comes into play here? The logarithm base a of m, that is itself a power. The answer to a logarithm is a power, and it's being raised to a power. So instead, we should multiply the two powers. This power p is multiplied by the log base a of m, which is the other power. The answer to the logarithm is the exponent. So when you have a power raised to a power, the two powers need to multiply, p times log base a of m. So again, they have a corollary where the exponent rule is related to the logarithmic rule. Can help us remember these. The next one is the quotient property. It says if I have the log base a of m divided by n, then I should be able to separate this as the log base a of m minus the log base a of n. This is similar to the exponential property. A to the m over a to the n is equal to a to the m minus n. We know that in exponents, if we have division by the same base, we're going to subtract the powers. Again, here, if we have division, we're going to subtract the powers. Similarly, multiplication turns to addition, division turns to subtraction, just like it did with the exponent rules. Okay. All right. These are really the main properties that we see right here, the product, power, and quotient properties. These are the properties that tie into expanding and compressing a logarithm. The bottom two are going to be a little separate, so let's take a look at these. The next one is the change of base formula. We saw this in one of the previous sections. If we have the log base b of m, we can rewrite that as the log base some other base a of m divided by log base same thing a of the previous base b. This does not have an analog in exponentials like the other rules did, but we've seen this previously as a way of going from one base to a new base a that would be introduced. And then other properties down here, these are some things we've seen in previous sections as well. We know, for example, that log base a of a is 1. A raised to the first power is a, so the exponent is 1. We've also seen previously that log base a of 1 is 0 for any base a. And then similarly, we can look at the properties here that say that log base a of a to the x is x. This is an inverse property here because these are actually both inverse properties right here. Logs and exponentials are inverses of each other, right? So these are our inverse properties. We know that when I have log base a of a to the x, these are going to undo each other, and it's going to give us just the x back, and so on. I also could think about this just as another way to think about it in case that inverse property is one that didn't come as naturally to you. You could think about this in terms of the power property. If you thought about it in terms of the power property, log base a of a to the x could be written as x times log base a of a. And log base a of a is 1, so that's x times 1, which is x. So again, either way, whether you're thinking about this in terms of inverses or in terms of the power property up here, we're going to come back with that x. All right. Okay, so we've got a bunch of properties here. Let's go ahead and use some of these. So in number 1, we're going to simplify or express the following in terms of sum and differences of logarithms. So we're being asked to expand into a sum and difference of logarithms. This is log base 3 of 81 times 27. It is a multiplication, so I'm going to separate this into log base 3 of 81 plus log base 3 of 27. In this case, both 81 and 27 are powers of 3, so we can evaluate each of these. We can evaluate log base 3 of 81. We'll get 4, since 3 to the 4th power is 81, plus log base 3 of 27. 27 is 3 to the 3rd power, and so we're going to end up with 4 plus 3, which is 7. It helps us to do this one using the sum and difference of logarithms because I recognize both 81 and 27 as powers of 3, whereas if I had multiplied those together first and gotten a larger number, I might not recognize the number that is 3 to the 7th power. Okay, in the next one, I have t as the base, so I separate this product to log base t of 8 plus log base t of g. Since I don't have a number for t, I'm not going to be able to evaluate log base t of 8. I don't know if 8 is a power of t, and I also cannot evaluate log base t of g, so that one's going to be done now that it's been separated into a sum. Part C, this is a natural log, so we're going to separate this into the natural log of a. It's again a product, so plus the natural log of b. And again, we've expanded this by turning that multiplication into a sum using the product property. All right. Continuing on to the next page, I've got the use of now the power property. So we've got log base a of x to the 4th. We're going to take our power down as a multiplication according to the power property. So this is going to be 4 times the log base a of x. Similarly, in part E, there's an exponent. We're going to take our exponent down as a multiplier. So instead of natural log of y to the 5th, it'll be 5 times the natural log of y. And also in part F, we've got this exponent. Bring that down using the power property. we'll have negative 8 times the log base b of q. The next set, G, initially doesn't look like a use of product power or quotient property, but I'm going to remember that the cube root of a is the same thing as a to the 1/3 power. So I am able to rewrite this using the power property, pulling that exponent down, and I'm going to end up with a 1/3 times the natural log of a. Radicals are just fractional powers. All right, part H, looks like on this one, we're going to get to use the quotient property. So that division, we're going to separate into subtraction. So we'll write this as log base t of 76 minus log base t of x to the 3rd. So that's our quotient property. Now, I'm not quite simplified, even though I've separated that quotient, because there is a power on this x. So we're also going to use the power property. So the final answer will be log base t of 76 minus 3 log base t of x. All right. In part I definitely have a product. As a matter of fact, this product contains 3 pieces, 6 times x times y to the 5th. So when I use the product property, we're going to split into the sum of 3 pieces, the log base a of 6 plus the log base a of x plus the log base a of y to the 5th, 6 times x times y to the 5th, each separated with the addition for a product. And then there is an exponent on y to the 5th, so we'll use the power property to move that down into the front, and we'll end up with log base a of 6 plus log base a of x plus 5, I forgot to write the log for a second, log base a of y. There we go. In part J, instead of a product, I'm starting with this quotient here, so we'll separate with subtraction. Log of p squared minus log of m to the 9th. The base on this log must be 10 since it's not written, so just have a log. And then we can use the power property to bring our exponents down as coefficients. So we'll have 2 times the log of p minus 9 times the log of m. In part K, that square root is over the entire quotient. So I could think about this original as being log base a of x to the 6th over p to the 5th to the 1/2 power. And I have a choice here about whether I would like to pull this coefficient down, this power down, or if I would like to use exponent rules and simplify this expression by applying the power to both parts of the quotient. I'm going to go that route because I notice that there's another exponent inside, and instead of having to do the power property once, I want to wait to the end and instead of having to do it twice, once at the beginning and once at the end, let's just do it once. So let's simplify before we apply those log rules. And I'll have this quotient simplified as, see, x to the 6th to the 1/2 will be x to the 3rd over p to the 5th to the 1/2 will be p to the 5/2. We're going to separate that division now into a quotient, or that quotient, I should say, into subtraction. It already is a quotient. Division turning into subtraction, log base a of x to the 3rd minus log base a of p to the 5/2. And then the power property, pulling these exponents down as coefficients. 3 times the log base a of x minus 5/2 times the log base A of P. Okay, similarly for part L here, we've got this cube root. We've got a whole bunch in the inside there that can be simplified. So let's rewrite the original log base A of something to the 1/3 power when I take the cube root and pull that up. But inside that fraction, there's a little bit of simplification that we can do. So let's take care of that here as well. We're going to look at the a to the 6th over a to the 3rd. That would reduce to just a to the 3rd in the top if I subtract those exponents. And also with our b to the 5th over b to the 8th, subtract those powers, and have a b to the 3rd in the denominator. Now when we apply this power to both parts of the quotient here, this simplifies to log base A of A over B. And I can separate that into a subtraction. Log base A of A minus log base A of B. One last thing to do here is, unlike the previous ones where I had a log base A of X and the argument was different from the base, in this case, my argument is the same as my base. So log base A of A can be simplified. That is equal to 1. So I have 1 minus log base A of B, and I don't know the answer to log base A of B. Okay. On the next page, we are now going to be doing the opposite. Instead of expanding, we are going to be expressing these as a single simplified logarithm. So we're going to be collecting terms into one logarithm. Log base A of 75 plus log base A of 2, that addition there is going to turn back into a multiplication inside of the logarithm. So I will have a single logarithm, base A, of the product 75 times 2. Since those are both numbers, I can write that as log base A of 150. So multiply the 75 times 2. Okay. Similarly, this one now is a subtraction. Natural log of 54 minus natural log of 6. So I can condense that into a division. So I'll have the natural log of 54 divided by 6. And I can complete that division. 54 divided by 6 gives me 9. So I'll have the natural log of 9. In the next one, I'm not actually able to work on the subtraction first. What I need to do first is work on the coefficients right here, pulling those back up as exponents using the power property. So let's pull those up. This will be log base A of x to the 2/5 power minus log base A of y to the 1/3 power. Then from there, I have a single logarithm, so there's no coefficient. I'm able to take care of that subtraction now, minus a single logarithm. And I'm going to end up with the logarithm base A of x to the 2/5 power divided by y to the 1/3 power. In the next one, we'll work on that same kind of idea. We've got our 2 coefficient, pull that up as a power. That 2 coefficient, pull that up as a power. So here I've got the natural log of x squared minus the natural log of the square root of x squared. We are going to apply inverse properties right here. We're going to say square and square root, those are opposites. So I've got the natural log of x squared minus the natural log of x. And then we're going to be able to condense using the quotient property, condense that subtraction into division. So the natural log of x squared divided by x. And that reduces, again, to the natural log of x. In part E, I'm going to use this multiplier of 3. It does need to be distributed. While we're distributing it, can we also apply the power property? So it's going to come up as a power on both of these. So I've got the natural log of 2x plus the natural log of x to the third power minus the natural log of y to the third power. That 3 would distribute, make it 3 natural log of x minus 3 natural log of y, and that 3 is going to come up as a power in both of those. Let's tackle this addition first. So if I condense these two terms that are being added, it's going to condense to multiplication. So I'm going to have the natural log of 2x times x to the third minus the natural log of y to the third. So 2x times x to the third is 2x to the fourth. Natural log of 2x to the fourth minus natural log of y to the third. And then we can finish by dealing with that subtraction and turning it back into a quotient. We have the natural log of 2x to the fourth divided by y to the third. Now in part F, I do have a subtraction to work with. So let's go ahead and deal with that piece and then we'll simplify. So our subtraction here is going to condense into a quotient. So I have log base A of A over the square root of x, and I need to divide that by the square root of A over x. I know that when I divide a fraction by something, that is the same thing as multiplying by its reciprocal. So when I multiply, that's going to give me square root of x on the bottom times square root of ax. So when I have to divide a fraction by an expression, same thing as multiplying by its reciprocal. So I end up with a divided by their square root of a square root of x. There we go. So log base a of a over, I can think about that denominator as a square root of x times a square root of a times a square root of x. What I'm trying to illustrate here is that the square root of x times the square root of x piece will come out as a regular x. So I've got log base a of a over x. And then this square root of a can we write as a to the 1/2 power? It's going to allow me to simplify and reduce those a's. This is a to the first power, and 1 minus a half is a half. So I end up with 1/2 as the exponent, a to the 1/2 over x. I have a single collected logarithm, but unfortunately it's not simplified. And it's not simplified because the base is a, and one of my arguments also has a base that is a. So unfortunately, we do have to re-expand this now. When I re-expand this, that subtraction is going to turn into log base a of a to the 1/2 power minus log base a of x. We are going to pull down this 1/2 power here to get 1/2 log base a of a minus log base a of x. And then we can simplify the log base a of a portion. That's going to be equal to 1. So 1 times 1/2 is 1/2 minus log base a of x. So my goal is to be able to express this with a single simplified logarithm. There's not a logarithm in this first place. It did simplify out, so I do have a 1/2 here, but I have a single simplified logarithm with it. So although we were able to collect, this also needed to be expanded because the base a was the base of one of my exponentials. We can do these problems in many orders, so this is not the only order that you could have done this problem. You also could have noticed that right away and expanded both of these first, then combined and recollected them. It's going to take several steps either way, so it doesn't matter which of those choices you chose to go with first. In part G, notice that there is a difference inside of this logarithm, and I'm not able to separate the logarithm of a difference. It has to be a product, a power, or a quotient inside the logarithm in order to separate. I'm only able to pull things together when there are two separate logarithms added, not addition inside of a logarithm. So when I have these two terms here, they are subtracted, so I'm going to be able to condense that subtraction into a quotient. This is going to be the log of x squared minus 5x minus 14 over the x squared minus 4, condensing into a quotient. And whether or not this can be simplified is going to determine what's going on. I've got this rational expression here that's going to be able to be simplified if I can factor and reduce. So let's give it a try. Let's see, 14, I can use 7 and 2. I'm going to need x minus 7 and x plus 2 to multiply to a negative 14 and add to a negative 5. And the bottom's a difference of squares. That's going to be an x plus 2 and an x minus 2. Looks like this is going to reduce. I can reduce the x plus 2 factors here. So my simplified answer is going to be the log of x minus 7 over x minus 2. All right, in the last one, we've got a lot going on. Looks like we've got a difference. And this 2/3 is going to apply to this eventually, but since it does apply to both parts, let's go ahead and take care of that quotient property first. So 2/3 times, sometimes I like to write natural log cursive, so I happen to do that here, natural log of x squared minus 9 over x plus 3 plus the natural log of x plus y. Very similarly, I think this is going to reduce if I'm able to get this factored. So 2/3 times the x squared minus 9 is a difference of squares. So it's going to be x plus 3x minus 3 over the x plus 3 plus the natural log of the x plus y. Similarly, we get some reducing happening inside of that first natural log. So I have 2/3 times the natural log of x minus 3 plus the natural log of x plus y. Now that the inside of those brackets have been simplified as much as possible, I'm ready to use the 2/3 as an exponent according to the power property. So now my natural log miraculously turned from cursive back to print. And so I've got natural log of x minus 3 to the 2/3 plus the natural log of x plus y. I had to pull that power up on this one before I was able to use the product property to turn that addition into a multiplication. But I'm going to end with the natural log of x minus 3 to the 2/3 times x plus y. condensing by multiplying the insides of that log inside of a single natural logarithm. Okay. In the last page here, we are now given the fact that log base A of 2 is equal to approximately 0.301, log base A of 7 is approximately 0.845, and log base A of 11 is approximately 1.041. I don't know what A is, but I don't need to know the value of A in order to be able to find the value of log base A of 2/11 and some of the other ones here. What I do know is because this is a quotient, the log base A of 2/11 is equal to the log base A of 2 minus the log base A of 11. And I've been told what the log base A of 2 is equal to. It's equal to approximately 0.301. And when I subtract the log base A of 11, I've been told that that is equal to approximately 1.041. So if I subtract these two values, I will know the approximate value for the log base A of 2/11. So the log base A of 2/11 is approximately negative 0.74. For 14, again, I don't know the log base A of 14 nor what A is, so the only way to be able to figure out this value is to figure out if I can make 14 out of the input values 2, 7, and 11. So I know that 14 is 2 times 7, and if I need to evaluate the log base A of 2 times 7, that's a product, I can separate that into the log base A of 2 plus the log base A of 7, and therefore this is approximately 0.301 plus 0.845. Oops, that was supposed to be a decimal place. So this value is going to come out as approximately 1.146. All right, continuing on, let's see if we can create a 98 out of these values, 2, 7, and 11. 98 is 49 divided by 2, and I know that 49 is 7 squared. So I can think about this as being log base A of 2 times 7 squared, right? If I multiply 2 times 7 squared, it is 98. Largely, this is a product, so we're going to separate this into log base A of 2 plus log base A of 7 squared. And now we have the power property, so we'll take our exponent down as a multiplier. And this is log base A of 2 plus 2 times the log base A of 7. Log base A of 2 is 0.301 plus 2 times log base A of 7 was the 0.845. So this value should be approximately 1.991. In the last one, this is a quotient. However, I do not know a property that's going to separate these back in. Instead, I actually do know what the log base A of 2 is 0.301. And I know that the log base A of 7 is 0.845. I don't need to use any property since I know those logarithmic values separately. So I can divide those. and this is going to come out as approximately 0.356. Alternatively, I could use the change of base formula on this, and I could, since I have a base A on both of these, rewrite this as the logarithm base 7 of 2. So that would actually be the exact value on this one, and that should be approximately equal to the 0.356. So let's check it. The log base 7 of 2 should be that same value. And again, it's approximately 0.356. Remember that these values here were approximate, not exact values. So there is going to be some discrepancy in the later digits in these answers, but they're both approximately 0.356. All right. Last example, number 4 here, simplify each of these. In part A, I've got an exponent. I can use the power property to rewrite that as a product. So that's going to be 3 times the log base A of A. And the log base A of A is 1. So this is going to be 3 times 1, which is 3. That's one way to think about this one. I also could think about this one in terms of inverses. And if I had thought about it first in terms of inverses, I might have noticed right away that these A's were going to eliminate and that my answer was going to be the exponent there of 3. So that's 2 ways to think about this question. Neither is more correct than the other. If we use that second idea in terms of inverses for part B, I'm going to say that log base t of t to a power, those are inverses. So the answer to this one is going to be the exponent of 2,713. We can also use the inverse properties in reverse. E to the natural log of x. The natural log's base is e, so those are going to undo each other. And they're going to return the argument, which is x to the third. 10 and log base 10 are opposites, so those are going to undo each other. They're going to return the argument, which is w. Log base 10 and 10 to a power are opposites. They're going to return the argument, which is negative k. And something similar is going to happen on this one, except for the fact that that radical needs to be treated as an exponent first. So if we think about this one as log base b of b to the, a square is a half power, so my power is 3 halves. Then these become inverses, and I'm able to return the exponent here as the argument 3 halves.